In this video, I'm going to be continuing on with Andrew's problem from the hockey homework document. And so far we have gotten through A and B, it's shown up here, and so we're going to be continuing to C. So I've copied the force diagram that we made from before so that we can use a fresh one for this, because this one's going to end up a little bit different from the one we did for part B. So let's dive right in. In this case, we are calculating the push force when the box is moving forward at a constant speed of 1.0 meters per second. So in the last problem, it was accelerating. We gave the rate of acceleration, and now it has reached its maximum speed, and we're just pushing it along at that constant speed. Because of this, because it's going at a constant speed in the same direction, we now know that the acceleration is 0, which means the net force is also 0. That's going to be really important for this as we start to figure out what the push force is going to be. So because this box is still moving, it's still going to have the same friction force on it, 1/10 of the weight. And as we said before, that's going to be about 54 newtons. And that'll be going in the back direction, so we'll make that negative. The push here, we don't necessarily know yet, and so we can put in a variable for it, so we can call that y, since we used x in the last problem. And as we've done that, we can see that we've only got the two forces here. We know one, we don't know the other. We do know the net force, so we should be able to find the unknown one using that algebraic kind of calculation like we did before. Again, when we add together the individual forces acting on our object, which are in this case negative 54 newtons for friction force, and whatever y happens to be for the push force, that will equal the net force, which we found since it's moving at a constant speed is just 0. In order to solve this, we'll just have to add 54 newtons to both sides. This way we'll get the y on its own. And that will leave us with y equals 54 newtons, in this case, positive. So we can also show that on the diagram up here just to summarize everything. So positive 54 newtons, and that will be the push force in this case. Because there was no acceleration, this was a little bit different from the last one, so we shouldn't be surprised that it's harder to push it while we're trying to speed it up than it is to push it just to keep it going at the same rate. So this is a reasonable answer in comparison to the 65 newtons that we had from the last question. Now that we have gotten through that part, D asks us when they get close to the other end of the rink, the boys release the crate and let it slide. How long does it take to stop? So from the beginning, this may not look like we have enough information to solve, but we do. We're just going to have to take it in using all the stuff that we've used before involving forces, but also incorporating some of the stuff that we know from the motion unit. A good place to start for this would be with a free body diagram. It's going to be a bit different from what we had before. So we'll start off with just the representation of our object and think about what forces are going on here. The crate's still moving right now, and it's moving to the right, so we know there's still going to be that friction force dragging it back to the left, opposing the motion. That's what friction does. And again, because it's going to be that same, we're still dealing with the same weight, it's still going to be a negative 54 Newton force. The thing that changes here is that because they have released the crate, there is no longer any push force. That means that the friction force is the only thing acting on this object at the moment, which tells us that the net force is going to be equal to it. When we have only one force acting on an object, that is going to be equal to the net force because there's nothing there to add to it or cancel out any parts. So we got that the net force is now going to be negative 54 newtons. We might be thinking about how this is going to be useful for us. We want to figure out how long it takes to stop. And so let's think about what we know. We already know that the crate is moving forward at 1 meter per second. So that was in part C, we got it up to that capping speed of 1 meter per second. We know that there is a force acting against it of 54 newtons. What we can find from that is acceleration. we can find an acceleration from the net force using the equation net force divided by mass equals acceleration. Plugging in that value we have for the net force, we can get negative 54 newtons divided by our mass, which was 55 kilograms, equal our acceleration. And that's going to come out to a negative value because we're dividing a negative by a positive. And it's approximately equal to 0.98 meters per second squared, units that we could find using dimensional analysis, seeing what happens when we divide the kilogram from the newton. So we've got an acceleration here. We have our velocity as it's moving on before this starts. If you think about it, we can also figure out what the final velocity is. We know that we're trying to figure out how long it takes to stop, which means that this is going to be one of those equations where we know the initial and final velocity. So it's stopping, the final velocity is going to be 0 meters per second. So to solve this problem, we're going to have to go back to our motion unit, where we have the equation for acceleration, which is equal to final velocity minus initial velocity over time. That's one form of the equation. We are looking for time here. We want to know how long this takes, which means that we could rearrange this to another form. You don't have to worry about the algebra because I would provide you with this alternate form. But this one is now solved for time. It's final velocity minus initial velocity over the acceleration. So this would be something that you'd begin on your equation sheet. And if you want to look back, it's provided for you on the motion unit equation sheet. Plugging in our values, we know that we are ending with a velocity of 0 meters per second is going to stop. It starts at 1 meter per second because that's what it's going at when the boys release it. We're going to divide that by the acceleration, which we found in the previous part, just the previous calculation, which is negative 0.98 meters per second squared. And doing this calculation should give us our answer in seconds. So what we see here, when we do 0 minus 1, we're going to get negative 1 meters per second on top. And we're dividing that by the negative 9.8 meters per second squared. So we're dividing a negative by negative, which means we should get a positive value for the time, which makes sense. We should be always moving forward in time, and it shouldn't be stopping before it starts to accelerate. So that makes sense for us. And when we do the calculation, we're going to end up with about 1.01 seconds, which, if we account for the significant figures, remember that the original value was 1.0, so I'll add that in. We would just bring that to two significant figures, which will be about 1.0 seconds. This tells us that it takes about 1 second for the crate to stop after they let go because of the friction force. So this takes us through all of the questions for Andrew's idea, and now you'll need to go on to try to apply that to Daniel and Gabe's ideas using the same kind of reasoning. They will be a little bit more complex, but the ideas behind them will still be the same. So do your best and good luck with them.